Picture this, you're at a bus stop standing in line waiting for your turn to board. The first person to arrive is the first to get on the bus. This everyday scenario perfectly illustrates a fundamental concept in computer science known as a queue. Welcome back everyone. Last time we explored stacks, a data structure great for managing tasks in a last in first out order. Today we'll flip the script and dive into a structure that organizes data in the exact opposite way. The queue. Think of a queue as a real lifeline of people waiting for something like a bus. You can only add new arrivals to the end of the line and serve from the front. In computer science, a queue works exactly the same way. It's a collection of elements where you add items at one end and remove items from the other. Queues operate with two main actions. Enqueue, which adds an element to the end, and Dequeue, which removes the front element. Just like in our bus stop line, you always add at the end and remove from the front. Queues follow the first in first out principle, or FIFO. This means the first item added to the queue is the first one to be removed. Just like the first person in line is the first to board the bus. Queues are essential in many computing scenarios, ideal for situations where tasks or data need to be managed in a first in first out order. Queues are perfect for task scheduling, ensuring tasks are processed in the order they arrive. This maintains fairness in the system, but it isn't always efficient. More on this in the next section. Imagine you're watching your favorite show on an OTT platform or a YouTube video when suddenly the dreaded buffering wheel appears. What's happening behind the scenes? Let's explore how queues help manage this buffering process, especially in situations where data arrives faster than it can be processed. When you're streaming a video, data packets arrive in rapid succession from the server. These packets, like frames of a video, are stored temporarily in a buffer, essentially a queue before being processed and displayed on your screen. In video streaming, as each data packet arrives, it is enqueued into the buffer. The buffer holds these packets in the order they arrive, ensuring that the video plays smoothly and continuously. When the video player is ready to display a frame, it dequeues the packet from the front of the buffer, keeping the stream uninterrupted. This buffer, or queue, ensures that even if there's a temporary slowdown in your internet connection, the video stream continues uninterrupted as long as there's enough data already queued up. So, the next time you watch a video online without interruptions, remember it's the queue at work behind the scenes, carefully managing the flow of data to ensure a smooth and continuous experience. To the next use of queue. Imagine there is an explorer in a maze looking for a hidden gem. He wants to find it as quickly as possible, but the maze has many twists and turns. How does he ensure not to miss any path and find the gem efficiently? As our explorer starts the search from the entrance, he marks his starting point and checks all the immediate paths leading from it. To keep track of the rooms to explore next, he adds each room's label to the queue. This way he ensures no path is overlooked. The explorer checks each room thoroughly before moving on to the next. By using a queue, he keeps track of the order in which rooms need to be explored. This way he explores all possible paths from each room before venturing deeper into the maze. The explorer finds the hidden gem in one of the rooms. Thanks to the queue, he explored the maze efficiently without missing any possible path. As soon as the gem is found, the explorer exits out of the maze using a secret door of the chamber. This search strategy, using a queue to explore each room level by level, ensured that every possible path was covered, leading our explorer straight to the gem. And just like that, using a queue helps solve problems efficiently even in the most complex mazes. Queues are also fundamental in managing printer jobs, ensuring each print request is handled in the order it was received. Queues are indispensable in computing, managing tasks in first out order. They optimize task scheduling, handle data buffering, assist in search algorithms, and much more. Their simplicity and orderliness make queues an essential tool in many applications. Besides Enqueue and Dequeue, there are two more key operations in a queue that are front and IsEmpty. Let's explore the operations of a queue. Enqueue adds an element. Dequeue removes the front element. Front views the front element without removing it, and IsEmpty checks if the queue is empty. Notice we focus on what these operations do, not how they're implemented. That's why a queue is considered an abstract data type. As a user, you don't need to know the internal workings. You just know that it follows the first in, first out principle. While an abstract data type ADT focuses on what operations do, a data structure focuses on how to implement them. Let's dive into the implementation of a queue. There are two primary ways to implement a queue that are by using an array or a list. Let's begin with an array-based queue. We use two pointers, front and rear, to keep track of the positions where elements will be dequeued from and enqueued to, respectively. When the queue is empty, both front and rear are set to -1. Enqueuing an element adds it to the end of the queue. In an array-based implementation, this inserts the element at the index pointed to by rear. This operation is efficient and takes constant time, big O1. Just like stacks, queues have a fixed size when implemented with arrays. Trying to add more elements than the array can hold causes a queue overflow error, indicating the queue is full and no more elements can be added. Dequeuing removes the front element from the queue. The element remains in memory but is considered removed from the queue. The front is incremented by 1, making the operation constant time, big O1. Trying to remove an element from an empty queue results in queue underflow, an error that indicates there are no elements to remove. Front allows us to view the front element without removing it, keeping the queue state unchanged. This operation also takes constant time, big O1. IsEmpty checks if the queue is empty. It returns false if the queue has elements and true when front equals -1. This simple check is performed in constant time, big O1. These operations are enqueue, dequeue, front, and IsEmpty that define our interaction with a queue, ensuring data management in a first in, first out order. In this session, we explored the fundamental concepts of queues, starting from their basic definition and moving through why queues are so important in various real-world scenarios. We then discussed queues as an abstract data type and finally delve into the nitty-gritty of implementing a simple queue using arrays. But queues don't stop here. In our next session, we'll take our understanding a step further by exploring more advanced types of queues, like the circular queue and priority queue, each with its own unique characteristics and use cases. Have you ever wondered how to make the most of your memory space while maintaining the efficiency of a queue? Well, the circular queue comes to the rescue. We'll see how circular queues elegantly solve some of the limitations we faced with simple arrays. As we conclude today's session on queues, remember, every data structure has its place and purpose. By understanding their strengths and limitations, you become better equipped to tackle any computational challenge that comes your way. Thank you for joining us today. Stay curious and keep exploring. Happy coding!